I now call upon Assistant Professor Mr. S. Rudramurthy, Assistant Professor Mr. Charnath from Department of Mechanical Engineering, Kingston Engineering College, to introduce our next speaker.
Good afternoon, everyone. I welcome all the participants for session two on day two. It's an honor to introduce Dr. Bhramara, Professor, Department of Mechanical Engineering, JNTU, College of Engineering, Hyderabad. Dr. Bhramara is so passionate about teaching and research, and she is much interested about the issues related to the education technology. She has experience of 21 years in this teaching field. She has received research grants from many funding agencies. Her research interests include heat transfer, nanofluids, and development of energy efficient processes. Her current research is on experimental investigation to determine the effect of nano lubricants on performance of vapor compression refrigeration systems. She has guided two PhD students and many PG students. She has published more than 95 papers in Refid and Scopus Index international journals. Dr. Bhramara has organized several national and international conferences as well as workshops. She has established refrigeration and air conditioning labs, turbo machines lab, and research lab in her department. She provides consultancy in thermal design verification, cooling load calculation for various air conditioning applications, and thermophysical properties of different fluids, including nanofluids. Dr. Bhramara has delivered a guest lecture in the field of heat transfer, nanofluid heat transfer, computational fluid dynamics, alternative refrigerants, thermodynamics, exergy analysis, outcome-based education, and research methodology. Currently, she is holding an administrative position as a training and placement officer and professor and in charge of alumni affairs in JNTU Hyderabad. I welcome you, ma'am. Now I give the virtual dais to Dr. Bhramara to share her. Thank you.
Thank you for nice introduction. Before starting with the presentation, may I know the composition of the participants we have and the number?
Ma'am, almost 90 participants, actually 130 participants have registered, but
Okay.
90 participants are in present today, and they are almost from 18 states, and almost most of them are doctorates.
Okay, great, great.
And 80% of them are concerned with thermal.
Okay,
Right.
okay, sure, thank you. So I'll switch off the video just to make the network in a smooth and regular way. So I'd like to share my presentation now. So I hope you all can see my screen. Can I just have a confirmation on that? Can you share the? Can you see my screen? No.
Not at shared.
You can't see it now? Okay.
No.
I don't have an option to share the screen actually. Can you enable the share the screen? I do not have the share screen option actually.
Ma'am, you have to share the screen, ma'am.
I don't have the option. I don't have the share screen option here. You have to enable that to me.
நீங்க enable பண்ணணும். Can you enable? Okay. இல்லையா? இது இருக்கு இல்லையா இந்த ஆப்ஷன்ஸ்? ஆமா. இது chat ஓபன் பண்ணு. ஓபன் chat. இருங்க இதெல்லாம் க்ளோஸ் பண்ணிடுறேன். அதுதான் முன்னாடியே வர சொல்றது அவங்கள. இது பக்கத்துல chat. இது பண்ணிட்டு அவங்க இன்க்ளூட் சிஸ்டம் மாடியூல் கொடுத்தாலும் டைரக்டா வந்துரும். அவங்களுக்கு அந்த ஆப்ஷனே இல்லன்றாங்க. காமிங்க சார் இந்த ஆப்ஷன் ஸ்கிப் பண்ண சொல்லுங்க. Ma'am, can you find an option near next to mic, ma'am? You could find 3 dots.
Yeah, I see the 3. Yeah, I see 3 points here, but I don't have option to.
Can you find open share screen?
Now I don't have.
Video.
Initially, when I started, I saw the share screen option. Now I am not seeing that option.
Can you reconnect, ma'am? Can you again log in, ma'am?
Okay.
Yes. Again.
ஒரே நிமிஷம் டெஸ்ட் பண்ணி பார்க்கலாம்.
இத மட்டும் க்ளோஸ் பண்ணுங்க ஸ்பீக்கர்.
Now I have. Now I have. So.
Yes, ma'am. Can you try, ma'am? Can you open share your screen, ma'am?
I'm trying now. Can you see it?
Yes, ma'am. Now it's okay. Fine.
Great. So good afternoon, all. So this is about the Exergy analysis of heat transfer process. Since the beginning of the workshop, I understand that you are going through the how to perform the Exergy analysis of various kinds of interactions that happen in any given thermodynamic systems. So I exclusively have considered the heat transfer processes. That is one thing, and secondly, I have made the presentation as a fundamental presentation, which would be very much helpful for the faculty members who are pursuing their PhD. Okay, so in that aspect, I have prepared my presentation. So if you have any concerns, you can we can discuss it at the end of the presentation. So now coming to the difference between energy and exergy, because they both sound alike, but there is a lot of difference between energy and exergy. And you know that energy flows into and out of the system along the paths of mass transfer, heat transfer, as well as the work transfer. These are generally the 3 interactions that happen in any given thermodynamic system, be it a closed system, open system, or isolated system. There is a possibility of these things. Some of these things would not happen in some of the systems. So accordingly, we have classified the systems as closed system, open system, and isolated system. And we also know that energy is conserved. Okay, and whereas if it comes to exergy represents the quantitatively it represents the useful energy. So it is energy, but it quantitatively represents a useful energy of the given system or given state. It represents the ability to do or receive the work, or you can also say define exergy as the work content of the great variety of the streams that pass through the system, namely the mass, heat, and work. And the importance of the exergy has come, and it remained in research. The reason for that is the attribute of the Exergy, which is nothing but it for the first time it has made it possible to compare on a common basis all these different interactions. Okay, you have the Exergy that is entering and leaving with mass, Exergy that is entering and leaving with work, Exergy that is entering and leaving with heat. So now you have a common platform called Exergy, based upon which you can compare the net Exergy that is destroyed through a system. So now you have some common basis. Before that, it was not like it. So now slowly coming to understand what Exergy is. So you know that the reason why I have discussed the first law, second law efficiency and exergy of different processes, the presentation is lined up like this. The reason for that is whenever you are performing the exergy analysis of the any given system, you need to have the thorough understanding of all the basic laws of the thermodynamics and also the fundamentals of the heat transfer as well as the fluid mechanics. And you can see that the exergy analysis how clearly a interdisciplinary subject with so much amount of the inputs that are needed to actually perform the exergy analysis. So to start with, you know that the first law analysis is very commonly known as thermodynamic analysis. Okay, so you also know the first law applied to a closed system is given by if you have a system here. So, okay, I hope you can see it. 1 second. So if you have a system here, you have certain queue taking place and certain work is taking place. You know that these interactions are expressed using this first law, which is applied to a closed system where there are no mass interactions. Now, if you look at the first law applied to a open system, and you know that the first law applied to an open system is represented by the mass balance as well as the steady flow energy equation. And when you apply the first law to a cycle, it is given by the algebraic heat interaction, the net algebraic heat
एक्सक्यूज मी मैम, आपका
yeah,
ये जो प्रेजेंटेशन मूव नहीं हो रहा है
क्या नहीं हो रहा है?
Ma'am, slides are not moving.
आपका जो स्लाइड्स मूव नहीं हो
Slides
रहे
are
हैं,
not
फर्स्ट
changing.
स्लाइड जा रहा है.
You are still at the first slide.
Yeah,
Yes,
ma'am.
ma'am.
I have actually moved from first slide to first law analysis. You can't see it?
Now it's moving, ma'am, but we cannot see your presentation mode. We are only able to see the slides.
Now making it in a presentation mode. Can you see it?
No, ma'am. Actually, you need to share the presentation video.
What I have to do?
Please stop share and again share the presentation mode.
Okay. No, I don't see the stop sharing option also in this. Yeah. So I'm trying to share again.
Yes, yes, ma'am.
Okay. So can you see now?
Yes, yes, ma'am. You can proceed, ma'am. Maximize your screen, ma'am.
Yeah. Okay, so the first law analysis, when it is applied to different types of the systems and also thermodynamic cycle, we use the same first law, which is the conservation of energy in different forms like this. Particularly when you are applying to the open system, we also need to do the mass balance in addition to the energy balance, okay, which is nothing but the applying the first law. Now, for example, if you take something like a, for example, turbine, okay. So if you take something like a turbine, I hope you can see my screen. Okay, and at the shaft you will get certain amount of the work output, and any given turbine system is for proper analysis you can say that there are no heat losses from the system, and you know that certain amount of the fluid at an enthalpy of H1 enters and the fluid at an enthalpy of H2 leaves. Okay, and we also make certain assumptions that this is just to show how to make the thermodynamic analysis. The assumptions that it is a steady flow process, you can do that. Any long running process can be assumed as steady flow processes, and we neglect the kinetic and potential energy changes. And you can say that because it is steady flow energy, mass is always balanced.
Ma'am, are you writing anything, ma'am?
Yes, you can't see it?
But no, we could not able to see, ma'am.
Okay. That's, I don't understand.
Can you jump to slideshow view, ma'am?
What should I do?
Slideshow view, ma'am. Actually, you have not turned up to slideshow.
I have made the slideshow view. 1 second.
Yes. Now it is okay, ma'am. The next slide it is coming.
If you see it like this and you can't see it, presentation means it's difficult, right? Can you see it now?
Yes, we can.
I think I made a mistake. 1 second. Let me. Yeah. 1 second. Yeah. I'm stopping the presentation again. Okay.
Yes.
I understood where the problem is. 1 second. Let me try it again.
Yes, ma'am. Thank you.
Can you see now?
Not at, ma'am.
No?
Not at Shad. Not at Shad, ma'am. Yes, ma'am. Now it's okay, ma'am.
Okay.
Fine.
Yeah. So you can see what I have written also.
Yes, ma'am. Continue, ma'am.
Yeah, so if you have neglect the kinetic and potential energy changes, you can write that H1 is equal to H2 plus work done, and what you get is the work and heat interactions you can obtain by doing what is called as um, what is called as first law analysis. Okay. I'll change the slide also.
Yes, ma'am. It is not. Yes.
So now,
Change it. Change.
yeah, I understand. Every time I have to go back and change the slide and go to the presentation mode. I don't know why it's happening, but it's happening like that. Anyway, so so now that is the first law analysis. In the second law analysis, uh, yeah, so in the second law analysis, it deals with the quality of energy, and you know that more specifically it is concerned with the degradation of energy during the process and about the entropy generation. Specifically, if you talk about the entropy generation, I don't know if you can see what I write now. You can use the TDS relationships. For example, TDS relationship du plus PdV, which we use for a closed system, and also TDS is equal to DH minus VDP, which we use for an open system to find the entropy generation ds. Okay, and we also know that this entropy generation is essentially given by the Clausius theorem. Okay, and we use these principles to evaluate the entropy generated as the process has taken place through a closed system or an open system. It essentially talks about the lost opportunities to do the work, and it offers how much amount of the scope is there for improvement. So you will first get to know about that in the second law of analysis. Okay, now coming back to Exergy. So Exergy, you know that it would be very desirable if you have a property which enables us to determine the useful work potential of a given amount of the energy which is at some specified state. Okay, this property of Exergy, which is also called the availability or the available energy. Okay, so it is represented by different ways for different types of the interactions. For example, if you talk about the work potential of the energy contained in a system at a specified state is simply the maximum useful work that can be obtained from the system, whether it is heat transfer or the work transfer. For example, if it is work transfer, it represents the upper limit on the amount of the work a device can deliver without violating any of the thermodynamic laws. For example, you can say that the work is function of the initial state, the process path and final state. So if it is so, what is the actual work, what is the reversible work, and what is Exergy? So I hope you can see what I am writing again. So when you say work is a function of the initial state, the path and the final state. Okay, so this is, you can say this as the actual work. And what is meant by a reversible work? Reversible work is a function of the initial state and final state, and the path has to be reversible path. Then we say that this is the reversible work. So if this is the reversible work, what is Exergy then? The Exergy is the initial path is same, it has to be reversible path, the work has to be the reversible, the path of the work or the path of the process has to be reversible path, and the final state has to be what we call as the dead state. So this is the useful work potential of given the amount of the work that is done through a given system. So now I hope you understand the difference between the actual work, reversible work and Exergy. If you can't see it, at least I hope you can now see it. Okay, so now if this is so, what is meant by the dead state? So dead state is the atmospheric condition. If nothing is specified about the dead state, you can take the dead state conditions as 1 atmospheric pressure and 25 degrees centigrade. For example, if I say that the final state is at 1 atmospheric pressure and the temperature is 30 degrees centigrade, it definitely is not dead state, and still you can run an engine between the 30 degrees centigrade and 25 degrees centigrade and get certain amount of the useful work. So if nothing is specified, we can consider these conditions as the dead state. Okay, so clearly the Exergy therefore is just not the property of is a property of the system and environment combination, and just not the system property alone. Okay, and the system, we say that it has zero Exergy if it is at the dead state. For example, if I take the ambient, if I take a system which is at a 1 atmospheric pressure and 25 degrees centigrade, the Exergy associated with that is 0. And you know that no work can be produced from a system that is initially at the dead state. Okay, and also the atmosphere around us contains a tremendous amount of the energy, but because the atmosphere is in the dead state, the energy it contains has no work potential at all. That's why we call it as a dead state. And now you can now say that the Exergy associated with the work, you can say as the work that can be obtained from an amount of the energy converted in a well-defined system under ideal conditions. That means applying the reversible processes using the environment only as the reservoir of heat and matter. Okay, under such conditions we say that that is the Exergy of the useful work content of the system. Okay, and so that is about the work potential. Now, if you talk about the work exergy associated with the kinetic energy and potential energy, the exergy of the kinetic energy is given by half v square per unit mass, where v is the velocity of the system relative to the environment. So this is something you need to understand. And if you say the exergy of the potential energy, it is given as Gz, where G is the acceleration due to gravity and Z is the elevation of the system relative to the reference level in the environment. So that means for the exergies of the kinetic and potential energies are equal to themselves and they are entirely available for the work. However, if you consider the internal energy and the enthalpy of a system, they are not entirely available, and you see that certain amount of the deductions do take place from the internal energy if it is a closed system and from the enthalpy if it is an open system, and it's not entirely available for the work. For example, if you take, I did not discuss about the closed systems because I hope that those were already discussed before. So now coming to the exergy of a flow system, if you take a flow stream, okay. So if you take a flow stream and something like that, you know that the energy content of the flow stream is given by H plus V square by 2 plus Gz, which is given by the steady flow energy equation. This is the energy content of the flow stream. Now, what is the exergy available with the flow stream? This entire enthalpy, you know that the V square by 2 Gz, they are completely available, so they are unchanged in this flow exergy term. But what happens to the enthalpy term? From the enthalpy, whatever is the dead state heat transfer values, that you have to deduct, and it will give that this is how the enthalpy at given state is not totally available. So what is available is H minus T naught into S is what available. Okay, this has to be deducted from again the dead state enthalpy, which is H naught minus T naught into S naught. So you can see that the enthalpy is not totally available, whereas the kinetic energy and potential energy, they are totally available. Okay, this is called the flow exergy. Okay, and I am sure you know how you calculate it. Okay, and then the exergy balance of the fluid stream, as it undergoes a process from state 1 to state 2, you can just take a net value of it, which is given by this. Okay, where the dead state values in both the psi1 and psi2 terms get cancelled, and it will result into the net exergy exchange as the fluid stream undergoes a process by passing through a open system and reaches from state 1 to state 2. Now, the continuation of the exergy of the flow stream is exergy transfer by mass. You know that along with the mass, it carries an amount of the energy. So, mass contains exergy as well as energy as well as entropy. So, the rate of exergy transfer to or from the system is proportional to the flow rate. Okay, so when a mass enters or leaves a system, it carries along with it some exergy, and it also leaves along with it some flow exergy. That's why we just have to multiply the flow exergy term with mass to know the exergy transfer associated with the mass transfer, which is nothing but the same. But if you know the amount of the mass transfer, you can calculate using this expression. Now coming to the exergy transfer associated with the heat transfer. So you know that the work potential in every time I am unable to write now because you could not see it. You know that the work potential is given by the Carnot engine running between the system which is at a given temperature and the reservoir which is at dead state. Okay, and you know that this Q X heat, which is nothing but the exergy of the heat, is nothing but the useful work. Okay, so I'll try to write it anyway here. So if you have a heat engine between the given temperature T and dead state T naught, we consider it as a reversible Carnot engine, okay, which is running between them. This is being the reversible engine. It will give rise to the reversible work, and the same reversible work I am calling it as the exergy of heat because it is between the given state and the dead state. Okay, so you can say that the efficiency of Carnot engine is given by the W reversible by the heat transfer. So the W reversible, which is nothing but in our case the exergy associated with the heat transfer, is given by Q into efficiency of the heat engine, and the efficiency of the heat engine is nothing but 1 minus T naught by T. So that's how we get the exergy associated with the heat transfer. Now, if you look at the exergy associated with the heat transfer between through a brick wall, let us say, which is something like our external wall situation, which is the external wall situation becomes very good example to explain most of the heat transfer processes. Let us say you have a medium 1 here, which is the probably outside conditions, the medium 2, which is probably the inside conditions. So you have the outside conditions have the higher temperature and inside conditions will have the lower temperature. And as the heat transfer takes place under steady state conditions, we say that the heat transfer taking place from the medium to the inside wall of the inside surface of the wall would be same as the heat transfer by conduction through the wall, and would be same as the heat transfer from the outer surface of inner surface of the wall to the inside medium. Okay, that's why Q is constant as you see under steady state conditions. But the same thing if you try to express in terms of the entropy transfer, because it is at the constant temperature, the entropy associated with it can be given as Q by T according to the Clausius theorem. So the entropy transfer associated at the medium 1 is Q by T1, and the entropy transfer associated with the medium 2 is Q by T2. Obviously, since T2 is lower than T1, the entropy is increased as it passes from medium 1 to medium 2, and you can see that this is the amount of the entropy generated. Okay, now if you, this is a very good slide which gives you the difference between the driving force that is needed for the heat transfer, namely the temperature difference here, the first one, and the heat transfer, how it takes place, which is remains constant, how the entropy transfer is associated, and how, what is the reason for the entropy generation, you can see it, and also the exergy transfer. Exergy transfer is given by 1 minus T naught by T1 into Q for the same Q and for the medium one.
Sorry to disturb, ma'am.
Ah.
Ma'am, your slides are not changing. Can you try again, ma'am?
You can't. I did not change the slide. What is
Yes,
the slide you are seeing?
it is, I think it is slide number 9. It seems exergy associated with work. Definition.
Oh,
It remains
exergy
same.
associated with the flow.
Yes, with work. Now it's changing now. Yeah, now it is changing.
Okay, so I'm showing it like this. Okay.
Yes, actually, you now in the slide number 13 it seems, but earlier we were in 8th slide. After then there is no change in your slide.
I have some problem with this Microsoft Teams, so looks
Okay.
like the issue is continuing here also. So
Okay,
what
ma'am.
I'll do is I'll not go by presentation mode and I'll show it
Yeah,
like
yes,
this.
ma'am. That would be better. That would be better. Thank you.
Okay. Yeah. So now you can see that in case of the exergy transfer, at medium 1 being higher temperature, the exergy associated with it is high value as you see it here. And because as you go to the medium 2, it being at the lower temperature, the exergy associated with it is lower, and you can see that this is the amount of the exergy that is destroyed, which is related to the amount of the entropy that is generated. Okay, so that is how the heat transfer, the entropy generated, and the exergy destroyed are connected. Okay, and for example, if you take, I actually could not do the problem, but you can now solve it on your own. For example, this is one brick wall, Okay, so under steady state conditions, the heat transfer through it, you can take it as some 1000 watts. And this is at 27 degrees centigrade. Okay, this wall and the inner surface temperature of the outer surface temperature of the wall is kept at 20 degrees centigrade. And this is the 0 degrees centigrade represents the dead state, and 5 is the temperature of the brick wall towards the other side of the medium. And you can calculate how much amount of the exergy associated with the heat transfer on the inner side of the wall, and how much amount of the exergy associated with the heat transfer on the other side of the wall. For example, if you can be patient with me, I'll just do one thing and I'll show you here. So you can say that the exergy associated with the this side is 1 minus T naught is 0 degree centigrade, which is 273, divided by 273 plus 27 into Q, and psi 2 is 1 minus 273 by 273 plus 5 into Q. And you can see that the exergy transfer is equal to psi 1 minus psi 2. So understood. So you can calculate the exergy transfer associated with it like this. Okay, with a simple heat transfer process, you can say that the heat transfer through a brick wall is like a closed system, and you can write it like this. Okay, and for example, if we are talking about the exergy balance for the steady flow stream, for example, towards the steady flow stream, the interactions will be through the heat, work as well as the mass. Okay, so if this is the amount of the exergy which is in, showing by the thickness of that arrow mark, and you can see how it is reduced by the time it comes out of the system, and you can calculate how much amount of the exergy is destroyed. Okay, for example, if it is a steady, for example, there are some several few interactions are there. You can calculate the exergy associated with all the interactions of the heat transfer as sum of the exergy associated with the heat interactions, and you have the exergy associated with the work interaction, and then you have the exergy associated with the flow streams, which along with the mass that it carries. Okay, mass in and mass out, and the amount of the exergy destroyed. So you can calculate the exergy destroyed based upon that. So if there is a single stream, you can calculate this as like this. Okay, single stream has single heat transfer or more than one heat transfer process. There is one work transfer, and this is the net amount of the flow exergy that has taken place. And by this energy balance, you can calculate the exergy balance. You can calculate the exergy destroyed. And you know that psi 1 minus psi 2 is given by this expression. Already we have shown it in the previous slide here, which is the exergy associated with the flow stream. Okay. So now I have kept one simple exercise for you so that you can understand how to deal with this exergy transfer processes associated with the heat transfer process and flow also. The reason why I have focused mainly on the open systems is, if you look at most of the thermodynamic systems, they are all open systems. Okay, so here I have shown you one example where you have some mass entering into some flow entering into the system. Okay, at a mass flow rate of 5 kg per second and at a pressure of 5 megapascals. This is something like, you know, some a typical case in power plant, and at a temperature of 40 degrees centigrade, and it comes out at a constant pressure. You can see that the pressure did not change, but the temperature is increased, so it is like a heater. Okay, and the surrounding ambient conditions are at T0. Okay, this is the dead state. T0 you can take it as 25 degrees centigrade, and you have the heat transfer entering into the process, which is one is at temperature 100 degrees centigrade, the other one is at a temperature 200 degrees centigrade, and you know the amount of the heat entering at 100 degrees centigrade, which is given by the 900 kilowatts,
you have to calculate the amount of the heat transfer coming into the system at 200 kilowatts. So firstly, you can calculate these things by means of the energy balance. And then after doing the energy balance, you will get all the quantities. Once you get all the quantities Q1, Q2 and all the other available values, then you can calculate the exergy associated with this heat transfer at T1, this heat transfer at T2, and you have a mass in and mass out. So you can clearly use this expression to solve a typical case of a heat exchanger. Okay, so once you are convenient with the evaluation of the exergy parameters of different process, different heat transfer process, now you are good to evaluate the second law efficiency. For example, if it is a heat engine, okay, the exergy supplied is decrease in the exergy of the heat transferred to the heat engine, which is the difference between the exergy of the heat supplied and the exergy of the heat rejected. Okay, that's how we calculate it, right? And the net work output is the recovered exergy. So once you know the net work output as a recovered exergy, I'll just write it down here, and then I'll come back to the normal mode so that you can understand it. So you can say that the second law, sorry. Whatever is the exergy recovered to whatever is the work obtained. Okay, so you can, one second. Yeah, so now you can see how you calculate the second law efficiency for a heat engine, which is the exergy supplied, the difference between the exergy of the heat supplied and the exergy of the heat recovered, and the work output is the recovered exergy, which is this, and the net work output is the recovered. So that's how you calculate the second law efficiency. For example, if it is a heat pump, the exergy supplied is the work input which you supply. This is what you have in the denominator is the work you supply. And the recovered exergy is the exergy of the heat transferred from the high temperature medium to a low temperature medium. And that's what we keep it in the numerator. And that's how we calculate the second law efficiency associated with the heat pump. Now, for example, if it is the heat exchanger. In the heat exchanger, what we do is, for example, you have the hot fluid and you have a cold fluid. So hot fluid enters at some temperature and leaves at some temperature, and hot fluid enters at temperature and leaves at another temperature. So whatever is the net exergy transfer associated with the hot fluid, and you can take the net exergy transfer associated with the cold fluid. So the ratio of that will give you the second law efficiency in case of the heat exchanger. These are typically the systems which you come across. Okay, and once you could able to calculate these exergy parameters for the heat transfer process as well as the flow process associated with the heat transfer. Okay, so you are now ready to do the exergy analysis for a given system. Okay, so by accounting for all exergy streams of a system, it is possible to determine the extent to which the system destroys the exergy. Okay, the destroyed exergy is proportional to the generated entropy. You know that, and the exergy is always destroyed partially or totally is the statement made by the second law of thermodynamics, and these are kind of typical facts about the exergy analysis. And the destroyed exergy or the generated entropy is responsible for the less than theoretical thermodynamic efficiency of the system, and that's what which you are calculating using the second law efficiency. Okay, and why do you have to calculate the exergy analysis? because you need to determine the exergy losses, what are the true thermodynamic losses in processes as well as in the systems. Okay, if you know them, you can look for the means to minimize the losses and optimize the driving forces. Okay, we'll try to take one example and see that. Okay, and by performing Exergy accounting in smaller or smaller subsystems, you can draw a map of how the destruction of Exergy is distributed over the engineering systems of interest. And you can, in this way, we are able to pinpoint the components and the mechanisms that destroy the Exergy the most. So you will be knowing these things, okay, probably by making a map of the things, you will be knowing where the Exergy is destroyed and all, but you also should have the understanding of where you can apply this optimization so that it is also economically beneficial. That also need to be taken care of while performing the Exergy analysis. And the real advantage in search of improving the efficiency is because you can do it by finite means. So for example, you have one heat transfer taking place into a system. The heat transfer does not take place as we show it in the thermodynamic system just like that. It has to pass through a mechanism through which it happens. So where and all the Exergy loss is taking place, if you could do that, the efficiency increases there by finite means. Okay, so because it tells us from the start how to allocate the engineering effort and resources. So where and all you can put the effort and where and all you can put the resources, you before even coming up with the real system, if this Exergy analysis could be made, this will give you a proper idea about how do we do with them. Okay, for example, I have taken one before that. Okay, so let's talk about the entropy generation minimization. Once you know how to calculate the Exergy destroyed and you can calculate the entropy generated. Okay, so Exergy destroyed is nothing but T naught into S gen, and S generated, the entropy generated you can calculate from that. Okay, and once you know that entropy generation, you can look for the means to minimize it. How? By placing the emphasis on identifying the mechanisms and system components that are responsible, namely for the thermodynamic losses and the size of these losses, which you can calculate by using the Exergy analysis. Minimizing the losses subject to the global constraints of the system, namely by minimizing the entropy generation, and minimizing the total costs associated with the building and operation of the energy system, and which is nothing but thermoeconomics. So you can see that how holistic this calculation of the Exergy analysis is associated with. Okay, and this is what we call as thermodynamic optimization. Okay, it is not about the totally cost optimization. What is the thermodynamic optimization is to be done in the preliminary stage of the design in order to identify the trends and the existence of the optimization opportunities. Okay, for example, you have designed a system with various heat transfer aspects, work transfer aspects, flow associated with that, and all these things. You take each and every aspect of it and you take the dead state conditions and you calculate the energy potential available with each of these process, and you can look for where this energy potential is being destroyed. If you could do that, okay, and if you could do that before the actual fabrication of the setup itself, if you could do that, pinpoint the aspects, and if you could do that, that would result into a proper design. Now, how do we minimize the entropy generation? So, to minimize the last power, okay, where the reversible work is fixed, right? Okay, you have the initial and final conditions are there, so the reversible work is fixed. Okay, so it is the same as maximizing the power output in a power plant and minimizing the power input in the refrigerator. So what is meant by maximizing the power output means maximizing the useful work means, or the reversible work means, it is maximizing the work output if it is a something like a power plant or a heat engine, and minimizing the power input if it is something like a refrigeration plant. Okay, this operation is also equivalent to minimizing the total rate of the entropy generation. Okay, to minimize the reversibility of the proposed configuration, the analyst the person who is trying to do must use the relations between the temperature differences and the heat transfer rates, and between the pressure differences and the mass transfer rates. Okay, so we'll take up one such case. To see how it is done. So this is one typical example. I'll try to make it a slide. I hope you can see it. So this is the typical example we find in power plants or any of the heat thermal systems. So as the title says, this is the model of a power plant with two heat transfer surfaces. And how do we maximize the work output, and thus how do we minimize the entropy generation? Okay, if you look at the case 1. Okay, if you look at the case 1, you have a heat reservoir here TH, from which the heat transfer has to take place through the system. So how the heat transfer take place? So there must be certain heat exchanger here. So when you say heat exchanger will have a overall heat transfer coefficient. It will also have the heat transfer area. So this CH represents the product of the overall heat transfer coefficient as well as the heat transfer area. Okay, and if you have the heat transfer area not properly designed, or the overall heat transfer coefficients of the heat exchanger, if they are not properly designed and calculated and arranged, then the heat transfer takes place through, as you can see, through a higher temperature difference. So when the heat transfer takes place through higher temperature difference from the reservoir to the system, okay, obviously you will lose large. So there is a scope for large amount of the entropy generation here, and there is a scope for large amount of the exergy being destroyed here. Okay, so this is one scope where you can work on to minimize it. So how do you work on it? Okay, you have to, as I said, CH. CH means you have it is product of the overall heat transfer coefficient and heat transfer area. So how do we take care of the heat transfer area? By maximizing the heat transfer between them. So you have to work on that, which is again takes the principles from the heat transfer as well as from the fluid mechanics and things like that. Okay, now if you look at the last case, the third case, here also you can see that in the heat rejection stage, where again another heat exchanger is involved, it is taking place through a higher temperature difference. So we normally show, while showing that from TH to the system heat transfer is taking place, but that heat transfer takes place through a device, okay, which is a heat exchanger. So you have to, there is large scope there where the generation of the entropy takes place and the exergy being destroyed. So you have to look for those means and you have to minimize them. For example, if you look at the central path, you have maximized the heat transfer area here, thereby try to reduce the temperature difference between both as much as possible, and you have maximized the heat transfer area in this case also, and thereby also you have reduced the temperature difference between both, and thereby you have increased the amount of you have maximized the work output. You can see the three cases, and you can see that in the second case the work output is maximized because you have identified that it is in the heat exchangers where the entropy is being generated. Okay, and you try to correct it and thereby reduce the temperature difference between the reservoir to the system between TH and THC, and similarly you have reduced the temperature difference between TLC and TL. Both you have considered, due to which you have maximized the work output. Okay, so this is I just quickly gave you, I actually tried to take up a couple of problems and try to solve along with you by actually doing them. But because I have an issue with my slides and my presentation, I am unable to do that. So from here, what I am trying to now explain is based upon if you look at most of the private engineering colleges where the students do not find the problems for doing their final year project within the college. Whereas just by knowing one simple concept called Exergy transfer or the Exergy analysis or the minimization of the entropy principles, if you by knowing them, you can make the students apply the same for the UG students. For example, you can, if you, most of the colleges definitely will have a double pipe heat exchanger because they all, those colleges which have mechanical will definitely have the heat transfer lab, and if you have heat transfer lab, you will definitely have a parallel and counter flow heat exchanger, the simple heat exchanger device. You can take two different cases. Okay, you can keep the cold water flow rate constant and vary the hot water flow rate, and then you can take this case two where you can keep the hot water flow rate constant and vary the cold water flow rate, and you can observe the changes in the entropy generation and the exergy destroyed in each case, and you can draw the conclusions based upon that. Okay, this could be one very good work where students would understand because in everywhere, wherever you are trying to calculate all these things, you have a means. Wherever you are looking for the scope, you can look for also the means to improvise the energy potential or minimize the entropy generation, and because it involves all the cases of the heat transfer and fluid mechanics as well as the thermodynamics. Okay, and you can further make the improvement on this work by changing the flow direction and compare the and make the comparative observation. For example, you can take a parallel flow heat exchanger, and then you can take a counter flow heat exchanger, and then you can see in which cases the exergy destroyed is minimized, and then you can add inserts and you can see whether the exergy destroyed is minimized or not. For example, you can also make it as a swirl flow and rotating flows. These are further developments on looking for the means in which cases the exergy destroyed can be minimized. It could come out as a very good work based upon which one can publish the paper also. Okay, and I just have, based upon the topic we have taken, I just have taken couple of research topics for the UG students. Okay, and other kinds of work you can take up for the UG students is that you can take a small capacity power plant nearby and perform the exergy analysis on it, because it involves, if you take a power plant, it has heat exchangers, it has turbines, it has compressors, it has pumps, you have all kinds of systems involved even if you take a small capacity power plant, and if you could make a exergy analysis out of it, you will understand to deal with all kinds of the energy interactions, or you can you know how to deal with all kinds of the interactions that take place in a given thermodynamic system, namely the mass transfer, work transfer, as well as the heat transfer. And also nowadays all of us are doing a lot of research with the heat transfer associated with the flow of nanofluids in a tube. So you can calculate the heat transfer associated with the flow of whatever is the base fluid, and then you can add the nanofluid of different volume concentrations to it, and then you can perform the experiment, and then you can also check the exergy analysis associated with the addition of the nanofluids. I don't think many people have done this problem, and this could become a very good work when you make it as a wholesome work. And then for the UG students, they can take up a laboratory model of vapor compression refrigeration system, and you know that it also has a compressor, it has a evaporator, and it has a condenser, it also has a pump. Okay, sorry, throttling device. So based upon all that, you can perform the exergy analysis of it, and so these are all very good works which is a good mixture of experimental work as well as the theoretical work, based upon which students can understand how to relate the theory associated with the practicals. So these are some of the references. I'm sorry my presentation has really ended very fast because of the the problem associated with the presentation. So what I tried to touch upon is
Just to give you a overall view of it. The need to understand the first law analysis before going up with the Exergy analysis, and the need to understand the second law analysis because entropy generated is nothing but the Exergy destroyed. And what is the Exergy? How do you calculate the Exergy associated with the work transfer, and what is meant by the actual work, and what is meant by the reversible work, and what is meant by the Exergy of work transfer? And then exergy associated with the kinetic and potential energy changes. Why we don't have these terms v square by 2 and gz, they don't change when you calculate the flow exergy, whereas the exergy associated with the enthalpy in the flow system or the open system and the internal energy in the closed system, they are reduced, they are not totally available. Okay, you can see that in case of the exergy of the flow system, and the exergy transfer associated with the mass transfer is just the extension of it. And then exergy transfer associated with the heat transfer, how do we calculate it? It is nothing but if you have a heat transfer taking place at a given temperature, it is like running a heat engine between that temperature and the dead state and calculating the useful work out of that. So that is nothing but the exergy associated with the heat transfer. And this particular figure clearly gives you when the heat transfer is taking place between two different temperatures, how the heat transfer is taking place and how the entropy transfer is taking place and how the exergy transfer is taking place. And we try to do the same for the taking one example of the steady flow energy system. I actually tried to solve this problem along with you, but because of the problem associated with the presentation, I could not do that. And then the extension of it is the, once you calculate all these things, the extension of it is to calculate the second law efficiency. Once you calculate the second law efficiency, it will give you the scope available for improvising the given system associated with these interactions. And then what is the purpose of this exergy analysis? How do we minimize the entropy losses, and how do we identify the scope, or how do we identify the devices, or how do we identify the interactions where the entropy generation is taking place, and how do we maximize the work output in case of the heat engine, and how do we minimize the work input in case of the refrigerators or the heat pumps, so that you can minimize the entropy generation. Okay, and we have taken up one simple case of heat transfer system, something like in a power plant where you have the heat transfer is taking place to a system through heat exchangers. Okay, you have the boiler there, you have a condenser there, and from the boiler you are supplying the steam to a turbine, so that's where you are supplying, which is, this is exactly to that, and you have the work output obtained here. And how do you identify that this is where the problem lies, and this you have to minimize. So you have to reduce the losses as much as possible to see that the work output is maximized. Once the work output is maximized, automatically entropy generation will be minimized. And based upon that presentation, I tried to show you a couple of some research problems for the UG students as well as for the PG students. So if you have any questions or if you want any further aspects to be discussed, I would be very glad. With the given constraints, I will try to do. Over to you, Professor Ganesh. Professor Ganesh?
Hello, ma'am. As there are no questions, I think we can continue. Thank you, Dr.
Sanjay, dear participants, if you have any queries, you can raise your queries to ma'am.
Yeah, you may please. Because I'm not sure how I presented because of the constraints I have.
Yes, ma'am. It seems that there are no questions from the participant side.
Okay.